dielectric materials. And now we want to learn about like metal dielectric interface, like a surface plasmons. And the textbook for this chapter is this book, Plasmonics. And one interesting fact about this book is that this book is written by Stefan Meyer. I guess he's now in University Imperial College, London, I guess. And this guy was my PhD advisor's postdoc, like long time ago. So at the very first page of this book, it says like, for Harriet Water, with thanks for the great time. So it's pretty interesting to see. Like, so this book was published in 2008 or something. And then Harry, my advisor, really liked this book because of this statement. And then he, bought like, tens of these books, and then gave like each of his student this book as a present. So I'm, this book is actually the book that I first learned about the plasmonics. It's not very well written in a sense, but anyway, it's kind of, it's easy to understand. So what we are gonna do is the same as we did before. The only difference is that now we are dealing with dielectric metal interface instead of dielectric air interface. So here, what we want to do is we have a metal here with permittivity looks like this, as we learned. And then we have dielectric with epsilon positive. And then when people say metal in optics, that means epsilon negative. Okay, if some material has negative permittivity, then people call this as a metal in optics. So wave solution, the same, like as we did, like E field is supposed to be e to the I k dot r minus omega t, and then kx, ky, kz supposed to satisfy this relation, right? And the propagation direction in this case is along x direction. And previously we set it to z, but here we set it to x because the book actually has this different convention. So, I just want to keep consistent with book. So now x direction is our propagation direction. And then y direction, we have like plane, no variation. So ky is 0. So what we want to find, the mode we want to find is the guided mode. So guided mode means the wave is propagating in this direction, but it's decaying in z direction, right? So that the mode amplitude is concentrated around the interface. So that condition is given by this, right? So K1z in the middle is minus I gamma 1, so that it exponentially decays as G becomes increases in negative direction. And similarly, K2z must be I gamma 2, so that the field decreases exponentially as G increases in positive direction. So if you draw the electromagnetic field in different coordinates, y direction, there's nothing. Z direction, it decays like this, right? So e to the gamma 1z, e to the minus gamma 2z, so that electromagnetic field is confined at the interface. And then along x direction, the propagation direction, electromagnetic wave is just oscillating so that it can propagate. So if I rearrange this term, then beta squared is equal to epsilon, this thing plus gamma 1 squared. And also this is for the region 1. It's region 1, where there is a metal. And then in region 2, where there is a dielectric. But for both cases, you can see because gamma 2 is, yeah, right. So because gamma 2 is a gamma squared is a positive number, so that beta is larger than the free space or the original K vector of the free space light. Okay, so how to solve this problem? Now I brought this equation again, like the Maxwell's equations, and I simplify this again. And then the reason why I brought this is to divide these equations into two, right? Because into two sets of equations. So first set is for TE wave, and second set is for TM wave. TE wave has whose electric field only have Y component. And then TM wave, the magnetic field only has Y component. So if electric field has only has a Y component, then this equation and this equation and this equation, 1, 2, 3. These three equations forms TE wave. Is relevant for TE wave. And then what's involving HY is these three is about TM wave. Okay, so what we are gonna do now is we check whether this the wave solution, wave equation, have TE and TM solutions. And if we do so, first TE wave. TE wave, as I said, these three equations are relevant. And then once you have a EY component, you can get HX and HG, which is this, right? And then we already set our wave form to be like this, right? Because it's, when G is negative, it's exponentially decaying with gamma 1. And then when Z is positive, where you have you're at the dielectric regime, it also exponentially decays with exponent with gamma 2. And then in the propagation direction, it has I beta e to the I beta x minus omega t, and also the same for the in the dielectric regime. So we know the solution should have this form, and then we put this equation into these two, and then set the boundary condition. Boundary condition is EY continuous, and then BX also continuous. BX is continuous. I'm sorry, is that true? Well, yeah, BX is continuous since assuming that material is non-magnetic, right? Well, what needs to be continuous is actually HX. HX is continuous, but BX is also continuous if these two materials have same permeability, right? So if you apply these two conditions, and then using this equation and these two equations, what you get is the amplitude A1 and A2 must be the same in both regime, and then gamma 1 and is equal to minus gamma 2. Okay, and this is a problem because gamma 1 and gamma 2 must be positive, both of these, in order for the mode to decay as it moves away from the interface. If one of the gammas are negative, then now let's say gamma 2 was negative. Then as G increases, it becomes an exponentially increasing function rather than exponentially decreasing function. which doesn't make any sense. Like it's, you know, it increases exponentially as it moves from away from the interface, which is not a guided mode. So there's no surface mode in this case. For TE polarization, there's no surface mode. Okay, that's what we can conclude. And similarly, if you go to the TM polarization, we use different set of equations. So now H has only Y component, and then EX and EZ can be obtained by these equations. Same ansatz. Ansatz is just the you know, kind of trial solution, and then same ansatz. And then if you have apply the boundary conditions, the same boundary conditions. Now, what you get is A1 equals A2, which is fine. And the ratio of gamma 1 and gamma 2 is equal to minus epsilon D over epsilon M. Okay. And one good thing is that epsilon D, which is the dielectric permittivity, is always positive. And then metallic permittivity is negative. So that minus epsilon D, epsilon M, this entire thing is positive. So there's no problem, right? So that this solution can be satisfied. So if you apply that solution, so this relation can exist. And then if you apply that to like, apply that with the wave equations, you get the dispersion relation here. Okay, so the beta can be written like this. So how did we get this equation? Is easy. Like we get this from the boundary conditions, and from wave equations in medium 1 and medium 2, we know that gamma 1 squared is beta squared minus epsilon 1. This, right? So epsilon 1 is metal, and then gamma 2 is epsilon 2 is dielectric. So we have 3 equations, right? And then by using these 3 equations, you can remove gamma 2 and gamma 1 from the set of equations, and you get the relation between beta and omega like this. And one important thing here is that epsilon D, the dielectric function of dielectric medium, may not be dependent on omega, but here epsilon M is dependent. So epsilon M is 1 over omega P squared minus omega squared, right? So if you actually draw the dispersion relation, it's like this. Okay, so this is the real k vector, and so the solutions looks like this. And then there's no solution, no propagating solution in between these regime. But here, you know, as I kind of explained in the photonic crystal lecture notes, you have an imaginary K solution. Okay, and this position where your K diverges can be found like this. And then this condition is called a surface plasma frequency, which is lower than the plasma frequency by factor square root of 1 plus epsilon D. Okay, and from these equations, we can find the important implications. First one is that this dispersion is called surface plasmon polariton, and then surface plasmon polaritons, its K vector at the same frequency, its K vector is always longer than the free space K vector, right? Which means its wavelength is always shorter than the free space wavelengths. So in that sense, surface plasmons are smaller than the free space light, which means it has a shorter wavelength. And it's a very important property. You can learn later on. It is really important that surface plasmons are smaller than the free space light, so that you can squeeze your light, a surface plasmon, into a very small volume, which is useful in the end. And another thing that you can notice is that if you think about the slope of the dispersion relation, which is the group velocity, it's always lower than the free space light. So this slope is equal to c, the speed of light, right? So surface plasmons are slower than free space light, and that's also always the case. And at low frequencies, as you go to a lower frequency, surface plasmon dispersion approaches to the light line. So the light line and the surface plasmon becomes almost the same. And then at the surface plasmon frequency, you see here, surface plasmon has 0 group velocity and infinite wave number. Okay. And then because of the last sentence, last statement, people were very, very excited about the surface plasmons, because they thought, okay, if we have a surface plasmon, then does that mean we have make light very, very slow, so that we can almost making light stopped at a certain position? And there's another interesting question is, if we can achieve infinite wave number, that means infinitesimally small wavelengths, right? So that, or then maybe we can make kind of localized light into an indefinitely small volume, so we can store light in a, let's say, in an atomic spacing. Maybe that's possible. Okay, so that was why people got interested about these plasmons at first place. But this is not possible, of course. It's kind of, it's basically too good to be true. And why this is not possible? Why we cannot get 0 group velocity, and why we cannot get infinite wave number or infinitesimally small wave length? That is because metals are always lossy. So in this scheme, we ignore the loss. So here we assume epsilon of metal is 1 minus omega p omega squared, right? So it's always real number. There's no loss. But in reality, epsilon m is actually not simply this, but you also have some loss term, imaginary loss term, and that's inevitable. Okay. So if we take into account, oh, sorry, I probably explained this first and then introduce loss later. But anyway, if we take into account loss, it becomes like this. The equation, the dispersion relation becomes like this. So now if you look at this, K vector, even though it's right at the surface plasma frequency, K vector never goes to infinity, right? And also, and like at high K vector, you also have a high imaginary part, which is loss, right? So these high K vector and high loss always comes together, makes us difficult to utilize these surface plasmons. And yeah, probably I should have explained this first, like why it has a slow growth velocity, but probably I can explain it later on next Tuesday.